So yesterday we started our section on sequences and series, and today we're going to continue talking a little bit about properties of convergent sequences. So recall a sequence was a list of real numbers, and a convergent sequence was one that, well, it converged to a real number. What did it mean to converge to a real number? Well, the real number was A. Then the sequence converges to the real number if what? What was the idea? How did it converge to a number? It had to, okay, closeness, this is a word. All right, it had to get close and it has to stay close. And how close? Infinitely close or arbitrarily close, right? Now, did you just say arbitrarily? I love it. Love it. Okay. So we wrote down that a sequence AN converges to A, right, some real number, if, good morning, the limit as n went to infinity, right, of the terms AN equaled A, and we gave a definition for this limit, right? Informally is what we just said. It's right that the sequence gets arbitrarily close and stays arbitrarily close to A. And then we wrote down a formal definition, had a little Greek letter epsilon. It was all fun. Okay. And we even gave a few examples of a convergent sequence, one of which, for instance, was a sequence half, a fourth, an eighth, a 16th. Right? That converged to 0. Right? And then you also had sequences that didn't converge to any real number. And you remember what we called those? Divergent, exactly. Right? So we had convergent sequences and divergent sequences. I just want to introduce a little shorthand notation. In this case, where you have a convergent sequence and it converges to the real number A, right, instead of writing down this limit expression, we'll sometimes write it like this. We'll say you have a sequence AN, and we'll just write a little arrow and then write what it converges to. Right, so the sequence AN converges to A. So, for instance, if you have the sequence 1 over 2 to the n, where n here goes from 1 to infinity, right, what did this converge to? To 0, right? As n grows large, this fraction grows small. In fact, it grows arbitrarily close to 0, and it will stay arbitrarily close to 0. Okay, so that's a nice little short way to write it. Okay. So when we talked about the limit as something went to something of a function, right, we had a whole bunch of limit properties. And all of those limit properties that are held for functions are going to hold for sequences. Okay, so I'll write down a few of these things. We won't prove it. The proofs are the same as they were before. Let's just get a good feeling for these things. So for instance, all right, well, I guess I need to give you a couple sequences. So let's let AN and BN be convergent sequences. Okay, a convergent sequence is a sequence that converges. Oh, okay. So what if you considered now a new sequence? Right. Oh, I guess I don't need the brackets here. I'll use parentheses. Okay, let me write down a new sequence. And the nth term in my new sequence is just AN plus BN. Okay? That's how you can add two sequences. Right? You just line them up. Okay? And in each of the first terms, you add them. Second terms, you add them. Third terms, you add them. Not me, Adam. But no. So you can get a new sequence. Right? For instance, when we had let's take this sequence, right? You have 1, 2, 3, 4, and so on. we have another sequence. How about we'll let it be -1, -2, -3, -4, so forth. What do I mean if I say I'm going to add? I don't mean sets here, right? I really mean sequence. Okay. What do I mean to add these two together? Right? If I add them together, I just do it term by term. 1 plus minus 1, 0. Okay, and actually, right, this is a rather nice result, right? You just get 0, 0, 0, 0. Okay. Okay. Now, these sequences don't actually satisfy this criterion, do they? Are these convergent sequences? Now, what's actually the limit of this sequence? Infinity, right? Remember, we also defined what it meant for the limit to be infinite, right? It's a divergent sequence, but it diverges to infinity. And what do you think this one should diverge to? Negative infinity. Okay. So what I'm writing here actually has nothing to do with this limit property I'm going to show you. I just want to show you what it means to add two sequences. Okay, so this would be the nth term in the sequence you get if you added these two sequences. Okay. And what would you like the answer to be? Right? What should be the limit of the sum of these two sequences? Yeah, adding up their limits, right? The limit of a sum, it would be nice if that would be the sum of the limits. Right? And that's exactly what happens. Another way to write this is to say, okay, if AN converges to A, and Bn converges to B, this is if, then the sequence AN plus Bn converges to A plus B. Okay, so you can prove this. The proof is the same as it is for functions, basically. Okay. There's nothing very special here about plus. You could do minus just as well to subtract two sequences. No problem. You can multiply two sequences, right? How do you multiply two sequences? Just do it term by term, right? Everything's always going to be term by term. Okay, so the limit of a product is the product of the limits. And, oh, Dina, you gave me a nasty look. Yeah, the dot. Yeah, at some point in your mathematical life, you will stop using the x symbol for multiplication and start using the dot. One good reason for that is simply that we use x's too much as variables, and it looks really bad to write x times y. It can get very confusing, especially because in the old days, if they wanted to write a quadratic down, do you know how they would write the quadratic? All right, we would write something like ax squared plus bx plus c. They would write axx plus bx plus c. Yeah, they would write this. But if they were going to do a cubic, they would write x cubed. But for x squared, they would write xx. Yeah, this was this is kind of strange. But I mean, well, I know at least in the 1600s and 1700s they were still doing this. I'm not sure when they stopped doing that, but they had their reason, I imagine. I don't know what it was. In any case, yeah, so we don't use this anymore. We always use our times, the dot for a times. Except when we take multivariable next term, and these are vectors, and then that becomes the dot product and not multiplication. For every rule, there's an exception. Okay. And then, well, what do you think the last thing should be? division. Now, of course, is there maybe a subtle problem with division? Yeah, if the denominator is 0, right? I could divide, this sequence by this sequence just by dividing term by term. But if I had a 0 somewhere, then I have a real problem, right? So have to account for that somehow. If, for instance, well, let's say we wanted to put here divides. Okay, we'll just put divides everywhere. The divides, of course, we can't do A over B if B is 0. Right? So if this sequence Bn converges to 0, then you can't do this. Right? If you're looking term by term, then there may be some zeros. And if you do have a 0 in the B side, you just kind of have to toss out that term. Right? You just don't look at that one. Right? You just look past it. Right? Now, what do I mean look past it? Okay, well, this actually brings up a point. Let's put this on the side. Okay. We know that if I start with the sequence a half, a fourth, an eighth, a 16th, and so on, that this is going to converge to 0. Yeah? But what if I throw some garbage in front? Let me put minus 12 and 100 and 10 to the 8th. Right? Just throw some garbage in the front. What does the sequence now converge to? Still converges to 0, right? Would it matter if I put more garbage in front? Why not? Right? What does convergence care about? Okay, you got to get close and stay close. Yeah? But how far do you have to go out to do that? Right? Well, just some point, right? There has to be some point where it starts working. Okay? Convergence somehow doesn't care about what happens in the beginning. Right? Think about it. Well, I don't want to get theological too much, but imagine a religion in which it didn't matter what you did most of your life, as long as at the end you repented and were a good person, right? And you okay, I accept whatever. Okay, that's what convergent sequences are like. Okay, they don't really care what happens in the beginning, as long as for a finite number of time you did garbage, but then you became a good sequence. Okay, then it's okay. Okay, that's what convergence believes. Now, you cannot do it for an infinite amount of time. That's the point, though, right? Because if it was an infinite amount of time, then it doesn't. You can't say, oh, it stopped here and then it started being good. Right? You can't be bad forever. You got to be good at some point. So the same thing is going to happen with these BNs and the 0 problem. Right? If that sequence converges to 0, of course you can't do anything to start. If it doesn't converge to 0, but it does converge, then eventually it has to stop having zeros in the sequence. Yeah? If it always had zeros, right, that's the bad thing. If it always had zeros, that's the bad behavior, then it couldn't be getting arbitrarily close to a non-zero number. Right? Even if that number was really, really close to 0, right, 1 billionth. But eventually it has to get much closer than 0 to 1 billionth. Right? So eventually you don't have any more zeros in your BN, and that's where you care about. Right? You just go out far enough so that you don't have to worry about it. Right? And that's the beauty of taking the limit as n goes to infinity. You just go out as far as you need to get rid of all the garbage, which in those cases is 0. Okay, so let's just say with allowances for division by 0. Okay, so here I just mean you have to make all these things that we just talked about, all these little assumptions. Bn doesn't converge to 0, and well, there's no problem otherwise if it. Yeah. Okay, so this is very nice, right? You can just it works exactly the way you would want it to. What if you choose a constant and you look at the limit as n goes to infinity of the sequence constant times an. Okay. So you take your sequence, and now I just multiply every term in the sequence by the same number. All right. So for instance, I might take this sequence and multiply it by, what's a good number to multiply by? 2. Okay. So 2 times this sequence. I can go 2 times 10 to the 8th, 200, minus 24, 1, a half, a fourth, an eighth, and so on. All right. Okay, so this is a new sequence. It's 2 times this sequence. All right. What does it converge to? And it still converges to 0 in this case. Yeah? In general, what is it going to converge to? It's actually going to converge to, well, you just take the original sequence and see where it converges to, and then multiply by that constant. In our case, it started at 0, so when you multiplied by 2, it was still 0. Okay? It works just the way you want it to. Okay? Here's just a silly one that we have. Let's say an is a sequence. It converges, but it's even better than that. For n greater than or equal to some fixed point, right? At some point m, an equals a. It actually just becomes a certain number all the time. What does the sequence converge to? What's that? A, yeah, right? At some point, it actually becomes A. It just goes garbage, 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 A. Right? It's just always A now. So what does it converge to? Well, it's getting awfully close to something. And it's staying awfully close to it, namely A. Okay. All right, so we get some of these nice properties. There's a few others that you could write down, but these are the ones we're going to be using. So again, you have a sort of linearity, right? Remember, linearity is when you can pull out constants and you can break up sums and differences. But you also have you can break it up over products and quotients. So this is very nice. All right, let's do a nice example. Are there any questions about this before I move on? No? Okay. So this is just going to be useful as we try to work through examples. We're going to be using these things behind the scenes all the time, right? You want to compute, what a sequence converges to. You're going to say, oh, yeah, first I can break it up and then pull everything out. And yeah, it's set up so it works the way you want it to. All right, so let's write down a rather obvious theorem. So let an be a sequence. Okay. I'm going to build a new sequence from the sequence. And the way I'm going to do it is just by taking every term in the sequence and looking at its absolute value. Okay. So for instance, if I did that to this sequence, nothing would happen. If I did that to this sequence, I would get back the original sequence. So I'm going to look at this sequence, right, where I take the absolute value of every term. And let's say that I know that that sequence converges to 0. Then I can conclude that my original sequence converges to 0. Okay, so let's see that intuitively. What does it mean that the absolute value of all the terms is going to 0? What does that mean? The absolute value of all the terms is going to 0. What's happening? It means that they are converging to 0, yeah, which means that they are, yeah, they're arbitrarily getting, well, I should say this, they're not arbitrarily getting close. They're getting arbitrarily close. And staying arbitrarily close to 0, yeah? Okay, but sometimes, right, the original terms could be positive or negative, but an absolute value, right, they're all positive and they're all heading in towards 0. Okay? So if that's happening, what must be happening to the original sequence without the absolute values? They must also be getting closer to 0, but they could be hopping back and forth, right? Some could be positive, some could be negative. Right? But they still have to be kind of shrinking in towards 0. Right? Which means they are getting close to 0. And they're getting arbitrarily close to 0. And they're staying arbitrarily close to 0. Right? Even if they're coming from the wrong side, positive or negative, we don't care. Okay? Because they're staying within that little ball around 0. Okay? So that's the idea behind it. Let's just for fun see if we can't prove this. Right? Using the actual definition of convergence. So let's just quickly recall that. So what does it mean that AN converges to 0? Right? Well, instead of doing 0, let's do A first. Okay, so let's recall this. AN converges to A. This meant the limit as n goes to infinity of AN equals A. Right? This meant if, okay, for any epsilon greater than 0, right? So as close as you want me to get, there exists a natural number n. Okay? I can go out far enough such that the distance between the nth term in my sequence and the supposed limit is less than epsilon. Right? I get close. And then for all n, right, greater than or equal to n, which means I stay close. Right? I get close and I stay close. Okay? So that was the definition. Right? That's what it meant to converge. So let's see what that means in this case. In this case, A is 0. So when A equals 0, right, we get, let's rewrite this. For all epsilon greater than 0, there exists a natural number n and n such that, well, the absolute value of AN minus 0. Okay, so I don't have to write anything. I can just close it off. Absolute value of AN is less than epsilon for all n and n. So if I wanted to prove this last condition here, right, that AN went to 0, I just need to show that the absolute value of AN becomes less than epsilon, right, for all n, whoops, greater than or equal to Rn. Sorry. Okay, on the other hand, we do know that this sequence converges to 0, which means that this whole thing is true, but I have to put absolute values around the AN, right? Because that's what the nth term of this sequence is, absolute value of AN. But what do you get if you take the absolute value twice? Same thing, right? Make it positive, you can't make it more positive. Right? So they're actually the exact same condition. Right? The condition for this to converge to 0 is exactly the same as the condition for this to converge to 0. There's no change, right? Because absolute value of the absolute value is just the absolute value. So they're actually the same thing. Okay, so that's really the proof. So it's actually very straightforward if you write down everything, and you don't have to make a hand-waving argument to do it. You can't say, well, you see, it's getting close on this side, and then it hops back and forth, but that doesn't matter because it's still getting close. You can just say, absolute value, the absolute value is the absolute value. That's all that matters. Okay, cool. So this is going to be useful. For instance, let's just write down a simple example. So let's define a sequence, and it's just going to be 1 over n. Right? N goes from 1 to infinity. What does this converge to? 0, sure, right? As n goes to infinity, these fractions keep getting smaller, right? As close as you want to 0, and they stay small. So that goes to 0. What if instead of having a 1 up there, though, I had a minus 1 to the n? Okay, and I have to warn you, you are going to learn how to deal with these minus 1s to the n's, because they're going to be all over the place in this section of the course. Okay? What does this minus 1 to the n mean? Why do I use this? Okay, well, let's write down some terms in this sequence. Okay? The first term is when n equals 1. When n equals 1, you get minus 1 to the first power. What's minus 1 to the first power? It's just minus 1, right? Raising to the first power doesn't do anything. So you get minus 1 over, well, n equals 1. You get right, minus 1 over 1 or 1. Or minus 1, right? Okay, what about when n equals 2? When n equals 2, you get minus 1 squared, which is 1, over 2. So you get a half. Okay, what about when n equals 3? Then you get minus 1 cubed, which is negative 1, right, over 3. So negative 1/3. Okay, what's the next term going to be? 1/4, negative 1/5, right, 1/6, so on. Okay. So you see what happens, right? This minus 1 to the n is in there to alternate the sign. Right? It's going to go back and forth, positive, negative, positive, negative, positive, negative. Okay? That's why we use this minus 1 to the n. It's a good way, it's a very short way, right, of saying let's alternate the sign. Okay, we're going to use that a lot. So if you get used to it. By the way, let's say I wanted to alternate the sign, but I wanted the first one to be positive, not negative. How could I fiddle with this to work that out? Well, I don't want to start at 0 only because you can't divide by 0. But we can do something like that. We can modify it a little bit so we do start at 0 if you like. Well, I have to do everything in terms of my natural numbers. Right? I'm still going to use this, but I can just change this exponent, actually. I could do negative n, and what would that do? So the first one would be minus 1 to the minus 1 power, which is the same as 1 over minus 1 to the 1 power, which is 1 over minus 1, which is still minus 1. So it still didn't solve our problem. What's that? You could square it? Okay, so if we squared it, then you'd get 1 squared, which is still 1. So we still have minus 1 to the 1. Oh, put a minus sign out here. Okay, so Kaiwei's thinking do this. Well, that'll certainly work. Right. Can we simplify that expression a little bit? Watch this. Minus 1 to the n. That's the same as minus 1 times minus 1 to the n. Well, which is minus 1 to the n plus 1. Okay, we just shift everything over by 1. So that's going to be the nice way to do it. So this one would be 1 minus a half plus a third minus a fourth, and so on. So this is going to be a useful little trick here, right? If you want to alternate it and you want it to start, if you're always starting at 1, for instance, right? If you want the negative sign to be first, just put a -1 to the n. If you want it to be second, then put a -1 to the n plus 1, or n minus 1. Either one will work. Okay, you just got to shift everything over. Okay. What does the theorem that we just proved tell us about these sequences? Okay, so the theorem we just proved had something to do with the absolute value, right? So if you take the absolute value of these terms, right, then and it converges to 0, then the original sequence converges to 0. What's the absolute value of these terms? Right? So let's see if I did that. What's the absolute value of this? Well, the first thing that you have to know is that absolute value is really, it behaves very well. It's going to break up over quotients and products. Yeah. Let's see. So they're jumping around, right? They're certainly hopping back and forth. Right? But they're still getting close to 0. Right? So let's see. Now, the absolute value is, at least with respect to multiplication and division, is very nice. You can break it up.
Is that a T or is it just random sharp line?
Where are we looking?
In the numerator of minus.
On this side? This? Oh, that's gunk. Sorry about that. Yeah, this is gunk that I can't get off. Okay, so first you can break up an absolute value on a division, right? You can just take the absolute value of the top divided by the absolute value of the bottom. And it also works with exponents. You can pull those out. Okay. So what's the absolute value of -1? Well, it's just 1. And you raise it to the nth power. Still 1. So this is 1 over, of course, the absolute value of n. Remember, n is running from 1 to infinity, right? So these are all positive numbers. So just 1 over n. Right. So the absolute value of this sequence, right, is actually just the original sequence we wrote down, which converges to 0. And what the theorem says is, if you take the absolute value of the sequence and it converges to 0, then your sequence converges to 0. So that has to converge to 0. Right? So this thing goes to 0. And for the exact same reason, this other one we wrote down, right, where you start with a positive instead of a negative, that has to go to 0. Right? So this is nice, right? You can take your sequences, and if they alternate, they do nasty things, they have sign problems, right? Just take the absolute value and check. And as long as you're talking about converge to 0, that's enough. You don't have to worry about anything. Now, would this be true, this theorem, if I was converging to something other than 0? Could I make this a little bit stronger? Right? Let's say the absolute value of my sequence converged to 100. Could I conclude that my original sequence converged to 100? Can you just argue, well, you see, if it's the absolute value is converging to 100, then it's just hopping around 100, right? And so the original sequence must be getting close to 100. Is that right? Or can you come up with a sequence that converges to 100 in the absolute value, but not the original sequence? So let's say I have a sequence, an, right, such that the absolute value sequence converges to 100. does this imply that the original sequence converges to 100? Dina says no. Well, more specifically, she shook her head no. Why no? Give me an example. Give me a sequence that converges to negative 100. Okay, I like the way you're thinking. So give me the easiest possible sequence that converges to negative 100. Aha! So Dina suggests negative 100, negative 100, negative 100, negative 100. Right? What does that converge to? Yeah, remember that was the last property we had down here, right? Is that if eventually it stabilizes, then that's your limit. Okay, well this stabilizes immediately. So this converges to negative 100. What's the absolute value sequence? Well, absolute value of negative 100, absolute value of negative 100. So on, and of course this is equal to 100, 100, 100. And of course this converges to 100. Right? Okay, so well actually this isn't a counterexample to this. Right? Does it? Or no, it is, right? Because that's our original sequence, right? Okay, so this is okay. So yeah, so this original sequence converges to minus 100, but the absolute value sequence converges to 100, right? So this is not true. Okay, so there's something special about 0. Okay, and why is there something special about 0? Well, if you hop around 0, that's fine, but when you start stretching away, now you're hopping between 100 and minus 100. Right? It's got to hop back and forth, 100 and minus 100. That's a long way to hop. Right? It's not so hard to hop around 0, but from 100 to minus 100, this is quite a ways. Okay. Sehr gut. Questions? Preguntas? Cuestiones? All right, let's see. So in our last few minutes, let me just set the stage for tomorrow. So we're going to start tomorrow by not proving, but merely discussing something called the Monotone Sequence Theorem. And to talk about the theorem, I just need to give you a couple more definitions for sequences. So the first one is fairly easy. This is a definition of a bounded sequence. So and I want to do this, well, maybe a little more pedantically than I should. But let's say this. A sequence is positively bounded actually, let me give a name to the sequence. Let's call it AN. Sequence AN is positively bounded if there exists a natural number m such that AN is less than m, right? Or maybe we say less than or equal to m for all n. Okay, so what is this? What am I trying to say? I'm saying that my sequence, right, is always below some level. Right? There's some number that it's always less than this. For instance, our favorite sequence, a half, a fourth, an eighth, a 16th. Can you find, is that bounded from, is that positively bounded? Yeah, it's both positively bounded and, well, we can say negatively bounded. But we'll get to that in a second. Yeah, it's bounded, right? It's never above 1. Right? Actually, is that the best bound you can come up with? If it starts at a half and a fourth and so forth, is a 1 the smallest number that it never gets above? Right? remember, we can let it be less than or equal to. What's the best you can do? A half, right? We know a half is where it starts and it just goes downhill from there. Right? So m, the half is actually the best. Okay? But bounded doesn't care about the best. Okay? Bounded just says there has to exist some bound, right? And by the way, in such a case, in this case, we call m an upper bound. An interesting question, once you know that something is bounded, is whether or not you can find the smallest upper bound, right? Or we usually say the least upper bound. And this is something called the sup of a sequence, S-U-P, right? Or, well, that's the abbreviation. It's called the supremum, actually. So the supremum is the least upper bound. Okay. We can also write this down for being bounded from below, right? And it's called a negative. We say it's negatively bounded. Right? Although the misleading the terminology I'm using, because you can be negatively bounded by a positive number, right, on the bottom. Okay. So another way you say this is bounded from above and bounded from below. Maybe that's actually a better way to say it. Yeah, so maybe I just change it right now to avoid confusion. Okay, is bounded from above. I'll say that, and an is bounded from below if, well, we just have to change the m so it's now on the bottom side, right? If there exists a natural number m, actually it doesn't have to be. Let me make this real here. If it's true with an n for bounded from above, it ceases to be a very good tool when it's bounded from below, because now you can't talk about negative numbers anymore. So let's just make this real numbers. Okay, so there should exist a real number m such that an is always greater than or equal to m for all natural numbers. And in this case, we call m a lower bound. And again, it's an interesting question to ask. If you can find one lower bound, can you find a better lower bound, right? What's the greatest lower bound you can find? And that's called the infimum, as opposed to the supremum, right? That was the least upper bound. And that's usually written the inf of a sequence, INF. So, okay, so we're going to, of course, these bounded sequences are nice. They're a little easier to deal with. We know that they're not, say, going off to infinity. Right? And tomorrow we're going to define something called a monotonic sequence. And then we're going to see what happens when you have a monotonic bounded sequence. We're going to show that any monotonic bounded sequence is convergent. Well, I'll say it. I don't know if we'll prove it.